Good morning to all of you. Hello, am I audible? Hello, am I audible?
Yes, sir.
Okay. So, are there any questions, doubts? Yeah, okay. If there are no questions, so let me start. So, be now the I'm going to continue with the 2D elements heat transfer application. So, last class I discussed basically the element level governing equations and then one example, and in that example I had basically developed the written the element level stiffness matrix and load vector for two elements. So let me continue with the same. So oh, it is not writing, so let me close the hello, is my screen visible?
Yes, sir.
Okay, so we are continuing with 2D heat conduction problem. So if you remember, what we have done is now taken this rectangular fin, and this side the dimensions were, it's actually square, although I have drawn a rectangle. So this is 2 meter by 2 meter, and we have discretized this into two elements. So these are the nodes. We are considering three noded triangular element. So the nodes are, this is 1, 2, this is 3 and 4. This we said element number 1, this has element number 2, and the coordinates are, this is x axis and this is y axis. And we said that this edge is at 100 degrees Celsius, and from this edge there is a heat going out. More realistic is actually the convective boundary condition, but to simplify I have done this. So here Qn is equal to basically minus 2 watts per square meter. So we had done the, of course, the element level stiffness matrix load vector. So now I'm going to discuss the assembly. So I need the element level basically the data. So let me write that again. So if you look at element number 1, we had written the element level stiffness matrix. Finally we got as Ke for this element was Kh by 2, where K is thermal conductivity and H is the thickness, and this was 1 minus 1 0, and minus 1 2 minus 1 0 minus 1 and 1. So this is what we had got, and the F external is 0, and F internal we had written for this element as basically sum of two terms. So we had minus 2H and then 0 1 1, and then we had of course plus H into the, on this edge we considered the heat going out from the element. uh, heat coming in the element, not going out, coming in the element. So corresponding to that, we had defined this load vector as F1, no for element 1 as number 3, and then the center one was 0, and then we had F3 for element 1 as number 3. So this is we have derived in the last class. Similarly, if you look at the element number 2, so for element number 2, the stiffness matrix was finally kh upon 2, and that was 1 0 minus 1 0 1 minus 1 minus 1 minus 1 and 2, and f internal for the element was why I am writing this, because no we need this in the uh, assembly. So we will have this term, we had minus h, and then we had f1 2 element number 2 edge number 1, and then we had f2 2 comma 1, and the third one was 0, and then we had plus h. So you can refer back to the last class notes, you have all this f1 2 comma 3, and then this is 0, and then we had f3 2 comma 3. So these were the no element level matrices and vectors we had derived. So the next is assembly. So as you see overall, so basically if you look at the this conductance matrix, so there are basically four nodes, and each node we have temperature as a degree of freedom. So T1, T2, T3, T4. So there are four unknowns. So therefore this matrix will be of size 4 by 4. So we will have the vector as T1, T2, T3 and T4. And the right hand side, as you see, the external load vector is 0. So that is going to be 0. And then you have, of course, this internal load vector. So this is going to be overall the assembled system level equations in the discretization. So now first we let us take the contribution of first element. So as you see, the first element is defined. Please pay attention, because this is first time we are doing the assembly of two-dimensional elements. So far we have done only one-dimensional elements. So if you look at the local node numbers, we said that no, this is local node number 1. Yes, please.
Sir, can we take this KE of the
Yeah.
element 1 and 2 as a
Yes.
standard KE for rectangular element divided
No.
into.
No, you have to derive actually. So the way we had derived it, because this is specific to particular this geometry. We have taken the dimensions as 2 meter by 2 meter, and then we have discretized it in this manner. So you have to actually derive from the formula which we have used. That k into a into b transpose into b. So you will have to actually use that formula depending on the problem. So you know the formula for b, so you have to, depending on the dimensions and the element discretization, you have to first write x and y coordinates of all the three nodes, then define b matrix, and then the this conductance matrix would be k into area into b transpose into b into h thickness. So you have to use that formula. You cannot take this as a standard matrix.
Yes, sir, understood, sir.
Yeah. So now the assembly. So we first element is first node is local node number 1 is global node 1, local node number 2 is global node 2, but the local node number 3 is actually global node number 4. So if you look at the the stiffness here, so basically, the first column will go to the first column of the global system, second will go to the second column, but the third column of the stiffness matrix would actually go to the fourth column. And similarly, the rows, so the first row will go to the first row, second row would go to the second row, but the fourth row would go to the uh, third row will go to the fourth row of the global system. So now let us take the contributions. So the first row and first column, that is this element will go to the first row and first column. So let us take the kh upon 2 common, because in this case it is common in both the elements. So kh by 2 I am taking common. So then here you will have 1. Then this particular element will go to the first row second column. So we will have minus 1 here. But now this one, the third column will go to the actually fourth column. So here I'll have to add it here 0. So these are, the for the global system, these are the columns. So let me write that also. So here this is column number 1, column number 2, column number 3, column number 4. This side row number 1, row number 2, row number 3, and row number 4. So now that's the first row. Second row will go to the second row. So that is this element of the stiffness matrix will go to the second row first column. This will go to the second row second column. So 2 there, and then this will go to no the second row fourth column. So it would be added there, and then the third row here will go to the fourth row of the global system. That is, this will go to the fourth row and first column. So I will add here 0. Then this will go to the fourth row second column, so minus 1, and then this will be going to the fourth row and fourth column, so it would be added here. So this is where the contribution of first element conductance matrix is going. Now coming to the second element. So if you look at the second element, it is defined between global nodes 1, 4 and 3. So its local node number 1 is actually global node 1. Local node number 2 is actually global node number 4. And local node number 3 is global node number 3. So if you look at the first row, we'll go to the first row because it is global node 1 is same as local node 1, and but the second is second local node number is global 4. So the second row will go column will go to the fourth column of the global system, and then the third will of course go to the third column, because local third node is same as global node 3. So this will go to the third column, and similarly rows will go. So this will go to the first row, then this will go to the fourth row, and then this will go to the this is for this will go to the third row. So now let's take one by one. So let us take this first row and first column of the second element. So it will go to the first row and first column. So it will be added here. So you will have plus 1 here. Then you look at this 0. So this 0 will go to the first row and fourth column. So we will have to add 0 over here. So yeah, let me erase and rewrite again, so that so we had 0 no, the we had 0 already there, and then this is going to the this element. No, this element is going to the fourth row, so plus 0 there, and then the this element will go to the third row. So this is going to the fourth, whereas this will go to the third column. So you will have minus 1 over here. Then when you look at the second row of the second element, it will actually go to the fourth row of the global system, because second local node number is global node number 4. So this will go to fourth row and first column, so it would be added here. Then this will go to the fourth row fourth column, so it would be added here. So it would be plus 1 here, and then this will go to the fourth row and third column, so it would be added here minus 1. And then now this one, the third row will go to the global third row. So this element will go to this location, third row first column minus 1. Then this will go to the third row fourth column, which is minus 1, so it would be added here. And then this will go to the third row and third column, so it will go to this location. And we have not got anything here, so they would be 0. So this is the assembled conductance matrix. So this is how no the from the connectivity you have to decide that is where the contributions are going to go in the stiffness matrix, the conductance matrix. So now the external load, because Qg the heat generation is zero, so that is all zero.
Excuse me, sir.
Yes,
Sir, in the second element, as we
yeah,
have written 143, can we
yeah.
also write it in terms of 134
No,
going
no, no,
clockwise?
no. You cannot do that. Because the way it is defined,
Yes,
no,
sir.
we have taken the with the definition of B matrix, we have taken the the global node 1 as the local node 1, global node 2 4 as local node 2, and the global node 3 as local node 3. So you have to go in that sequence. You have to go 1 4 3, not 1 3 4. You have to go 1 4 3, and you have to follow this anti-clockwise sequence.
Yes, sir.
Yeah, you cannot go 1 3 4. You have to go 1 4 3. So now coming to the now the load vector. So let me take the first one. So first let me look at this. So I just said no, this minus 2h let me take inside. So we have seen already know the first row goes to global first row, second row goes to global row 2, and the third row goes to global row 4. So this will go to the row number 1, this will go to row number 2, this will go to row number 4. So we will have here 0 and then minus 2h, and in the fourth row then we will have minus 2h. So similarly, this one you will have in the it will be going into the first one. So I'm writing no for the first element first. So this is plus, you have h into f1 comma 3 will be going over here, and then the second will go to the second one, so which is already 0, so plus 0 will be there, and then the third one will go to the fourth row, so plus f3 into h, of course, 1 comma 3. So yeah, these are the contributions of the first element. Then going to the second element. So now you have first let me take this one. So this will go to again first row. So we will have plus h into f1 2 comma 1, and then the second will go to the fourth row. So that is this will go to the fourth row. So we will have plus h f2 2 comma 1, and then the third will go to the third row will go to uh, global row number 3. So we will be adding over here. So let me just put a 0 over here. So this is how it is going. So 1 4 and then 3. So this has gone to first row, this has gone to fourth row, and then this has gone to third row. Then similarly this one,
Excuse
so
me,
it
sir.
will, yeah, yes,
Isn't it should be negative, sir?
which one? Did I miss some minus
Element
sign?
2.
Okay, yeah, so the first one is, yeah, minus is there, yes, yeah, sure, yes. There has to be a minus sign, so let me correct that. Yeah, it has to be a minus, yes. So there is a minus sign here, there is a minus sign here. Thank you for correcting this. So then the next is this one. So this will go to the basically first row. So plus h af1 2 comma 3. 2 is element number, superscript in superscript, first number is element number and second is the element number. Then this 0 will go to the fourth here, so it would be plus 0, and then the third will go to the third row, so we will have plus here h af 2 comma 3. So this is the assembled system. Now let's so once we have this assembly, so essentially we are going based on the how we are considering the local node numbers and the relationship between global node numbers and local node numbers. Of course we follow the anti-clockwise sequence here, because the way we have written the areas and know the definition of area coordinates L1, L2, L3, so the local node numbers have to be in anti-clockwise sequence, so we will have to go in that manner. So while developing the element level governing equations for the second element, we started with this as a local node number one. So we are going in the sequence 1 4 3. It is also possible that you can go 4 3 1. So in that case, you have to x1, y1, x2, y2, x3, y3. You have to write accordingly, and you can go 4 3 1, or you can go 3 1 4. So accordingly, of course, the connectivity will change, and therefore the where the rows and columns of element level equations will go to the global system, that will change. So the logic, once you understand the logic, you should be able to do for the any sequence of numbers, but in the anti-clockwise manner. So once this is done, so then no next is the boundary conditions. So actually see, we are trying to learn the theory behind what is there in the FE packages. So if you kind of want to analyze the whole submarine or a ship, so you cannot obviously do manually. You have to use a package, and in that package you would be using these elements. Of course, the assembly solution of equations would be automatic through subroutines in the software, but this gives you an understanding that how the whole problem is going to be done. Of course, the simple problems can be done manually. So the boundary conditions, now if we look at the boundary conditions, the first is, we said no that this edge is maintained at 100 degrees Celsius. So this entire edge is maintained at 100 degrees Celsius. So the temperatures of node 1 and 3 are going to be 100 degrees Celsius. So that means T1 will be equal to 100 degrees Celsius, and T3 will be equal to 100 degrees Celsius. Then the second boundary condition is, now if you look at particularly basically, if you look at this particular term, now these are coming, this is from the first element, edge number 3. So if you remember, no, edge number 3 for first element was this was edge number 1, this was edge number 2, this is edge number 3 for the first element, and this is HF21 is for the element 2, edge number 1. For element 2, edge number 1 was this element 2, this is edge number 1. So basically they are the same edges. So you will find when we have written the expression, so if you look at this, HF1 1 comma 3 minus HF2 2 comma 1. So this was by definition, if you look at it, was h into integration along the edge 4 to 1, and it was x by 2 qn 1 comma 3 ds minus integral again along edge 4 to 1 x by 2 qn 2 comma 1 ds. So h is same, so either you write put a bracket over here. So you will see that this is q1 comma 3, this is qn 2 comma 1. So if you remember on this edge, when we talked about the element number 1, we said that basically q1 comma 3 is like this, and when we talked about element number uh, 2, so on this edge, this same common edge, we said this heat transfer is, so this is qn 1 comma 3, and this was qn element 2 comma 1. So these, because if there is a line source along this edge, going from 1 to 4, so along one edge 1 4, if there is an external heat source, that is, there is a heat flux applied per unit length, let's say along this line, or per unit area along this line, then no, there would be difference between this Qn21 and Qn13. But in this problem, there is no heat flux applied. So basically, Qn2 comma 1 has to be equal to Qn1 comma 3. So that means whatever amount of heat is going from element 1 to 2, that is this one, that has to be equal to the amount of heat going from element 2 to 1, that is this. So therefore, this term and this term would be equal, and therefore this would actually be 0. So that is one. And same thing if you look at no, this term over here.
Excuse me, sir.
Yeah, yes, please.
Sir, can you please explain the heat flux you were talking about? The heat flux, if present, what
Yeah.
will the value will change? Uh, what is that
So
heat flux?
what I was saying is that suppose we had no problem like this. So let us say one is that we have already taken some heat flux over here, and now this is a line, and say there is some line source. Maybe that there is a heat flow net, no, there is, it is connected to some heat source, let's say a heating element, and it's connected to an engine or anything like that. So we are idealizing that by a line. So let us say there is a net heat flux here, like this. Let's say this net heat flux is there. This is over the entire plate when I'm talking about, and let us say this is Q. So then this Q1 comma 3 minus Qn2 comma 1, that would be equal to Q. This would be externally applied known quantity. So for the current problem, this is actually 0. So if that Q is non-zero, then Qn1 comma 3 minus Qn2 comma 1 would be equal to Q. If the direction was in the other side, so let's say if it was in the other direction, in this direction, if this Q was in this direction, then in that case Qn1 comma 3 minus Qn2 comma 1 would be equal to minus Q. So in this case it is actually 0, because no, there is no externally applied heat source along this diagonal. So therefore this Q is 0, and therefore this difference is 0. So that is what I was talking about. Is that clear?
Yes, sir.
Yeah. So now
Sir, in what all cases it will be non-zero, sir?
it has, there has to be some heat source, so it would be given. So if you are given a problem, it would be given that there is a heat source along this line, and if nothing is given means it is 0. And the real life situations would be there has to be a heating element along that. So let's say an engine is mounted, and from the engine there's some heat coming, and that heat is whatever heat is coming is idealized as heat distributed along a line. So that would be kind of a situation. So it would be given. If you are given a no, it would be shown that there is so much of heat flux coming along this line, external heat flux. So so we similarly we look at, no, this term. This is also coming from the same basically Qn1 comma 3 and Qn2 comma 1. So this will also be 0. So if you look at H F1 1 comma 3 minus H F1 2 comma 1. That is, we are looking at no, first I already talked about. So that is 3, not 1. I'm sorry. So yeah, this is not 1, but it's 3. So this is 3, and this is also 3. No, that is 2. Sorry. So F3 1 comma 3. I'm talking about basically this minus H F 2 2 comma 1. I think there is one correction over here. I think if you remember, yeah, if you recall, no, look at, refer back the notes. The last class notes. This is 1 minus x by 2. I just mixed up something. So this is 1 minus x by 2, 1 minus x by 2. The conclusion is the same, but the same function is 1 minus x by 2. So for this it is, now if you take h common, and then integral again along edge 4 to 1, and then we have 1 no x by 2. So this I am just referring to x by 2, and then you have qn 1 comma 3 ds minus integral again 4 to 1, and then you have x by 2 qn 2 comma 1 ds, and this will be equal to again 0, as I said. So this term and this term is same, the same functions are same along that line, and since there is no heat source, so qn 1 comma 3 minus qn 2 comma 1 would be equal to small q, that is this q, which would be equal to 0. So this term is also 0. So these are the boundary conditions. So now ultimately what we see, that this is 0 and this is also 0. So you will find now that this remains as an unknown. No, this h into f 2 comma 3, this term, and this also remains as an unknown h into f 2 comma 3. So these two terms, so basically this was, I think I wrote f1, yeah, this came from from the second element. So first was minus and then second was f 2 comma 3 and then 0 here, and this was f3 here. This is f3, I think I missed that 3 over there. So now you will see that this is an unknown and this is an unknown. So these are two unknowns. So number of unknowns, if you see T1 and T3 are they are already known. So T1 is known, T3 is known, and T4, T2 and T4 are unknown. So the two unknowns are T2 and T4. Then the other two unknowns are this H into F1 2 comma 3 and H into F3 2 comma 3. So these are the other two unknowns. So there are total four unknowns and four equations. So again, like what we did earlier, first we can take equation number 2 and 4 and solve for T2 and T4, and then take equation 1 and 3, solve for HF1 2 comma 3 and HF3 2 comma 3. So that is how the solution will be there. So now if you look at the,
Excuse me, sir.
yes please.
Sir, can you just briefly explain why in the integral of HF3 1 comma 3 it is integral 4 to 1? Like it is of the node 3, we are going from 1 to 3.
So we if you remember, we had introduced a minus sign. So why for no, for element 1 we said integration from 1 to 2, so there q1 was 0, integration from 2 to 4 where q1 was minus 2, and then we said 4 to 1. So when we wrote 4 to 1, we took qn 1 comma 3, so that we kept as it is. But when we looked at the second element, so we went from 1 to 4, then 4 to 3 and 3 to 1, and this integral 1 to 4 we wrote as minus of no integral from 4 to 1. So that is how no this minus came. If you remember, no, this minus came because we converted this integral from basically 1 to 4. Instead of 1 to 4 we wrote it as integral from minus of 4 to 1. So that is how 4 to 1 came in both. In the definition of this integral 4 to 1, in the definition of this also the integral is from 4 to 1. So last lecture class, when you look at, when
Yes, sir. Yes.
we find that, so we converted the integral from 1 to 4 to integral from 4 to 1. So therefore minus sign, and that is why this minus came.
Yes, sir.
Okay. So now as far as the solution is concerned, so we need to, as I said, first we take equations 2 and 4 for T2 and T4. These are the temperature unknowns. But now only thing you will have to keep in mind, earlier the structural problems we solved, the specified degrees of freedoms were used to be 0, although they could be non-zero specified values also. But all the examples I took there, the specified degrees of freedom used to be 0. So those terms were no, just eliminated without any effect. But here T1 and T3 are non-zero values, specified values. So we will have to take their effect no, in the equations. So first we just let's take the equation 2 and 4. So you have kh upon 2 and equation 2 is -1, 2, 0, -1, and this is 0, -1, -1, and 2. I'm just taking equation 2 and 4, and this is multiplied with t1, t2, t3, t4. And the right hand side, if you look at, we have when we are taking equation, this will give us -2h, and this also gives -2h, because this term is, these two together are 0. So this side we have basically -2h and -2h, where h is the thickness of the plate. So now what we can do, since T1 and T3 are known quantities, so we can know T1 is 100 and T3 is also 100. So first term into T1 plus third term into T3 can be taken on the right hand side. So actually what you can do is take the T1 and T2 terms to the right hand side. So this side we will just left with the the second and the fourth columns. So we will have 2, -1, -1 and 2, and then we will have T2 and T4, and this is of course -2h, -2h. And now this side we will have k minus kh by 2 into T1 and plus 0 into T3. So minus kh by 2 into T1, which is 100, will go to the right hand side. So we will have, since T1 is 100, so by 2 will give 50, and minus minus will become plus, so we will have 50 kh. Basically, this kh by 2 into T1 is going onto the right hand side, because that is a known quantity. T1 is known, T3 is known. And then in the second equation, first is anyway 0 into T1, so that doesn't have any contribution, but the third will give you minus kh by 2 into T3, and when you take it to the right hand side, it will become plus kh by 2 into T3. T3 is 100, so it will become plus 50 kh. So now you see that there is a term on the right hand side due to non-zero specified values of T1 and T3. So obviously, these equations have to be solved. So now you can invert this matrix. So you would see that T2, T4, if you invert this would be equal to, you have to find the determinant of this matrix and then the inverse. So the determinant would be 1 upon determinant would be 2 upon 3 kh. You're just taking the inverse of this matrix, so which would become 2, 1. That means these are interchanged, and the sign of these is changed for a 2 by 2 matrix. So we will have plus 1 here and 2 here, and then this side we have minus 2h plus 50 kh and minus 2h plus 50 kh. So now you can solve these equations. So you would see that basically now if you multiply, so ultimately you can see that the solution will be, if you multiply this, so T2 and T4 will be equal to, if you multiply now this matrix with this and simplify the terms, so finally we'll have 100 minus 4 upon k, and second will also be 100 minus 4 upon k. So k is thermal conductivity. Depending on the thermal conductivity, the temperature of node 2 and 4 is going to be reduced by this 4 by k. So 100 and 100 is 100 is on the left hand side, and it would be 100 minus 4 by k, 100 minus 4 by k on the right hand side. So now we have to also find out the other two parameters. So that is, if you look at the, we can solve equations 1 and 3 for basically, these unknowns what we have over here in the assembled system. These unknowns, that is hf1 2 comma 3 and hf3 2 comma 3. So we'll have to solve for
So
f1.
can you please explain 100 minus 4k step?
That is coming from the solution. No, you just multiply this matrix with this vector. So you basically, both terms are same, no? So you get this 2 into minus 2h plus 50 kh plus 1 into minus 2h plus 50 kh. So that will become 3 into minus 2h plus 50k. So this 3 will get cancelled. So you will have 2 upon kh into minus 2h plus 50k. So when you multiply by this 2 by kh, this no, you
Yes,
will
sir.
get 100 and the other will get 4 by k. So it
Yes,
is
sir.
just a, yeah, multiplication. So if you look at now these terms, so you have we need to find this h into f1 2 comma 3 and h into f3. Yeah, that, yeah, it's 3 2 comma 3. So now that is, if you look at those equations, equation 1 and 3, so we have kh upon 2, and the first row is 2 minus 1 and 0, and third row is minus 1 0 2 and minus 1, and then we have, of course, now we got all the temperatures. So T1 is 100 and T2 is 100 minus 4 upon K, and T3 is 100, T4 is 100 minus 4 upon K. So this we have already got, and this side we have basically, this H F1 2 comma 3 and H F3 2 comma 3. So these are, now if you do the multiplication, no, this side it is straightforward multiplication. So if you do the multiplication, no, you would be able to, I know you can cross check yourself. You have to multiply this matrix with this vector. Finally, you will get two rows, and the first row would be equal to this, second row would be equal to this. So you will find that HF1 2 comma 3 will come out as 2H, and you will find that basically hf 3 2 comma 3 will be equal to also 2h. So essentially, the conclusion drawn is this is a simple problem. So we expect this solution. Why do we expect that solution? Because we had said that no, the heat removed from the left hand, no, the right hand side is 2 watts per meter square. So and we said that this edge is insulated, so there is no heat exchange along this edge. This is also insulated, so no heat exchange along this edge, and this edge is maintained at 100 degrees Celsius, so it would be taking heat from this side. So what it is giving you is that no, the heat uh, going from the no, the connected system this side, whatever is connected this side, from that the heat is essentially 2 watts per square meter. So if you take 2 watts per square meter, so essentially will have total heat as 2 into area would be this length 2 meter into thickness h. So it would be basically 4h and divide it into two nodes, so 2h and 2h. So you see that no, if we do everything correctly, we get the solution which is physically can be interpreted. So that is the total heat going from the connected system to this pin is 2h plus 2h, that is 4h, which is equal to the heat which is going out from the right hand side. So yeah, this completes the solution of this problem. Although this is a very simple problem, but it demonstrates all the steps of any 2D finite element analysis of any problem. And you can do any complex problem. You could actually, rather than specifying here, let's say a heat flux, you can give a convective boundary condition. You could have a convective boundary condition here also. You can have convective boundary conditions here. You can have convective boundary condition on this faces also. So this face and the backside face, so all those possibilities are actually there. So let me just hint you out about convective boundary condition on the right edge. So suppose if we
Sir,
have, so yeah,
sir, sir, the physical
yes,
interpretation which you are talking about,
yeah, so
2h
the
plus
what,
2h at each node.
so what I was saying is, so if you look at this edge is insulated here, this is insulated here, so only heat which is going out from this fin is this 2 watts per square meter. So the total heat which is going out is this 2 into this length which is 2 meters into thickness which is h. So total heat which is going out is actually 4h. So what we have got, no, these values, no, this quantity represents the essentially the heat total heat coming at this node, and similarly this quantity represents, this particular quantity represents the total heat coming at this particular node, node number 3. So the sum of those two is 2h plus 2h 4h. So that is equal to the total heat which is going out. So that means, whatever 2 watts per square meter in steady state condition is going out, that much of amount would be taken from this side. No, it would be connected to, let's say, engine or whatever. So that much of heat is going out from this. So our solution is consistent that we got no this HF1 2 comma 3, which is the total heat flux. So at node 1, total heat flux coming at node 1, and this is HF3 2 comma 3 is the total heat flux coming at node 3, and the sum of those two heat fluxes is 4H, which is equal to the total heat flux which is going, total heat which is going out of the this fin. Is that clear? So
Yes, sir.
Yes, sir. Yes, sir.
what I'm saying is, this side, this 2 watts per square meter is the heat. So if you look at the total heat, that is going to be 2 into 2 is the height into h is the thickness. So that is 4h. So we expect that from this side also it must be taking the same amount of heat. So now we have got, instead of course, this distributed heat flux, we have got the heat flowing at node 1. So the heat flowing at node 1, no, this quantity is basically your HF1 2 comma 3, and this came out as 2H, and the equivalent of this, no, the distributed, that is an unknown. We got HF3 2 comma 3. This is also equal to 2H. So this sum 2H plus 2H is 4H, which is equal to this. So you would see that the total heat which is removed from the basic no the say the parent system which is here, maybe engine or whatever, I know that that amount of heat is removed is equal to this heat which is going out from the spin. So now I just want to give you another homework problem. So you just try solving this. I will give you some hint. I will not do the whole thing. So now let us say there is a convective boundary condition on the right side. So this is a homework problem. So for the same example, there is a convective boundary condition on the right edge. Right edge means no, basically x is equal to 2 meters edge. The same problem. So only thing you will see, because if there is a convective boundary condition, so here we have no, in this I had given this heat flux. Now there is a convective boundary condition. So you will find that this Qn would be equal to, yeah, because it's a convective boundary condition, so the heat flux, heat per unit area, would be basically Qn on that edge is going to be minus beta times T minus T infinity. Where no, let us say the surrounding temperature T infinity is, let us say, 50 degrees Celsius, and beta is convective heat transfer coefficient. I am not giving its value, so you can work out the solution in terms of that convective heat transfer coefficient. So only what is going to change is the internal load vector in element number 1. That is the only thing which is going to change. The conductance matrix for element 1 and 2 would remain same, and the internal load vector for element 2 would remain same. Only thing which is going to change is the internal load vector for element number 1. So that is the only thing which is going to change. So I'll just show you how we can do that calculation. So if you look at element number 1, F internal for this element is edge 1. Anyway, the Q1 is 0. So when we are going along the edge 2 to 4, so basically x coordinate is fixed, y coordinate is going from 0 to 2. So we have discussed that while accounting for Q1 is equal to minus 2 watts per meter square. So it's the same thing. We will have H transpose into Qn into H into dy, that is along H basically 2 to 4. So for this x is 2, And the second of course is the same, that is integral from 4 to 1, and we have h transpose into qn 1 comma 3 hds. So that part remains same. So it's the only first term which is going to change. So let me call this as a first term, and let me call this as a second term. So now the internal load vector here is basically this expression is the same. We have done only thing is in place of q1 we substituted minus 2. Now we have q1 is equal to minus beta t minus t infinity. So that's the only difference. So now if you look at the first term, so the first term is integral 0 to 2 and h transpose evaluated at x is equal to 2, and qn is minus beta times t minus t infinity into h into dy. So now you can write this as, now what you can do, let us say that beta is a constant function, a constant term. Convective heat transfer coefficient doesn't change along edge no 2 to 4, that is y going from 0 to 2. So minus beta, let us take common out, and then we will have integral 0 to 2, and then you have two terms basically here. One is this h transpose into t no, and then of course we beta we have taken out, then this t is there, and then of course h into dy, that is one term. And then another term is we have basically this minus I have taken out. So the second term would be, let me write separately that term. So minus minus it would become plus. So plus we will have beta integral 0 to 2, and then again h transpose along x is equal to 2 into t infinity into h into dy. So this is what it is going to be. Now if you see, as far as this t is concerned, this is an unknown temperature. So we have to write this t as h into t dE. So when you look at the first term minus integral 0 to 2, we will have h transpose. Of course, this is along x is equal to 2, x is equal to 2. This t is also along x equal to 2. So we can write that as h into dE, and d can be taken out of the integration sign. Of course, this is along edge 2 to 4, so x would be equal to 2 along that edge into small h into dy into dE. And of course the second term remains as it is. Now essentially you have the same thing, beta integral 0 to 2, and then h transpose x is equal to 2 t infinity h into dy. So these remain same. Now if you keep remember, so this first term we have minus beta here, integral 0 to 2, and this h transpose along x equal to 2 for first element was we have already shown that 1 minus y by 2 and y by 2. And similarly, so this is transpose, h is 0, 1 minus y by 2 and y by 2. And into, of course, you have h into dy into dE, and the second term would become beta integral 0 to 2, and then 0 1 minus y by 2 y by 2 into t infinity into h dy. So you need to carry out these integrals. So now you have to multiply these matrices. So this is 3 by 1 and this is 1 by 3. So ultimately we'll get a 3 by 3 matrix. So if you multiply all these, so finally you will get, now you can multiply and do the integration. So that part you can do. So minus beta into h, you will get this 0 0 0. This will be 0 0. Here 2 by 3, 1 by 3. That is, you have to just do the multiply these two and then integrate each element of the matrix. So we will get this into dE, and plus the second term would be beta into t infinity into h, and this integral would be 0 1 1. So once you have this, now during the assembly process, you would see for the first element this would contribute to the conductance matrix. So in the element level governing equation for the first element, this has to be taken to the left hand side. So if you look at, no, that means when you look at the Ke for the first element, effective Ke, so let me say that Ke for element 1, when you look at, The right hand side, no, this is the load vector, internal load vector ultimately, and the another term of course would be due to this, which is same as what we have already discussed. But now the stiffness matrix is going to be modified. So that is going to be kh by 2. We already have this 1 minus 1 0 minus 1 2 minus 1 0 minus 1 and 1. This we already have. In addition to this, we will get plus this beta into h 0 0 0 0 2 by 3 1 by 3 0 1 by 3 2 by 3. So now this would be the ke for the element number 1. No, that's the only difference, and the this will remain as an internal load vector. It will remain on the right hand side, but this will go to the left hand side, and then you assemble and then impose the boundary condition whatever are there on the left hand side, and then solve the problem. So rest of the solution is going to be exactly same. Yeah, so I think, yeah, I want to stop here today. I have to go to Ames for some consultation. So I'm stopping the class 20 minutes early. But meantime, I have 2 to 3 minutes. So if you have any questions and doubts, you can ask. So the next class, that is on Saturday, I will be starting plane stress, plane strain elements. So again, structural mechanics, basically problems. So plane stress, plane strain elements, that is what I'm going to start in the next class. So if you have any doubts and questions in this, whatever we have discussed, you can ask. Hello, are there any doubts, questions on this, whatever we discussed? So this one you must complete the complete solution. T infinity I have already given as 50. So you should now assemble the equations, impose the boundary conditions that T1 and T3 equal to 100 degrees Celsius, solve for T2, T4, and then solve for those H into F1 2 comma 3 and H into F3 2 comma 3. So you should solve for all those. So from that you will be able to find out how much heat is removed from the engine or the source to which this pin is connected. Okay, so if there are no doubts and questions, I will stop you.
Excuse me, sir.
Yes, yeah, yes, please.
Sir, we started to solve the force internal. This whole
Yes,
thing
yes,
which we
right,
did
right,
for the
right.
second.
Yeah, right.
Yes, sir. So when we are doing for the force internal, we got a term for KE in our final term.
Yeah, right. The reason is that because now the boundary condition, if you look at, now it says this Qn is equal to minus beta T minus T infinity. So because why minus sign is because no, the Q1 is positive. The way we have defined Q1, Qn is positive towards the surface. So when I take T minus T infinity, I am assuming that the temperature of the fin is higher and the surrounding temperature is smaller. So the heat is going to go out from the fin. So that is why this minus sign. And since this boundary condition is dependent on this unknown temperature T, and this already we have no T transpose into Q1 in the the potential due to Qn. So we essentially get no T transpose into T, and that is why no this boundary term is also giving no contribution to the conductance matrix, the left hand side. So we started with F internal, but that F internal is giving rise to the contribution to the conductance matrix, also the left hand side, and of course this term what you have here. So since this is dependent on D, this has to be taken on the left. So that is how for the element 1, effectively this will be the stiffness matrix. Okay.
Yes, sir. Yes, sir.
So are there any other questions? So if there are no questions, I'm stopping here. Thank you all for your attention.